Hello and welcome to another video in the series about creating a compiler for a new programming language. Last time we created this abstraction that's called a function that allows us to not track the stack ourselves and have a bit more higher level looking code instead of just straight up assembly. Today I wanted to do something very quick. And I thought I would add ability to call other functions, and at least, or maybe like even simpler, just create a way to proxy like one argument function to another function and see how that goes. So for that, we will need to have to know like what is a call instruction. So we'll go here and see how code looks like. In particular, we will need, I believe, the absolute call. 64-bit mode. No, that's not what I want. Call near absolute indirect address given in stuff. This is call near. Call far. Absolute address given. So in 64-bit mode, if selector points to a gate, else rip relative instruction pointer. So let's just try to see what that would look like. So call keyword pointer, or like call RCX, or even better, call 34 1-2-3-4 1-2-3-4 1-2-3-4. So right now it's just trying to call like completely absolute address. Is it even possible? Operand type is much for. Should I do like this? No. I guess I cannot call like that. Well, I still should be able to do something like call RSP plus 10 or whatever, right? Yes, and I could call RCX. Call RCX. Yeah, that seemed to work. So that uses FF D1. So I guess it uses this version to call like this. So maybe that's what we will use. Let's try to add that one. We need our encoding file. We need to have new instruction. Let's just copy paste sub. That's fine. It's gonna be call. It's gonna be call here. And then we have extension type, which is opcode. Yes, that opcode is 2, and the only operand is register on memory, which is not something we had before, so it's a good thing for us to stress our matching code as well. Like this, and the opcode is not 83, the opcode is FF. Okay, so we have that. We still need to change this stuff to be call, and call. Good. Let's see if this builds. It does build. Now we need to have a test. So what would we want? At first, we could have a function that just calls the function that we pass to it, and that function does not accept any arguments, and then return something. And we actually have a function like this, right? So we can have this one. So let's create a new test. Should create a proxy function for no argument function. We take this constant one. Great. It will return us a constant number and not require any arguments. And now we want to say proxy type proxy. I have a new microphone set up, so it's a bit need to get used to how the keyboard is located right now. Proxy S32 is proxy, and this is make proxy no arg return S32. It's a bit of a mouthful, but this is what we'll go for. Okay, we have this proxy. Now we call it, and then we expect to still get 42. Let's create this make proxy no arg, and that proxy actually needs to accept our other function. Okay, so we need to create this. Actually, we don't need a separate separate type for this proxy, because the type of this proxy should be exactly the same as the type of the function that we are trying to call. So this is fine. That means we don't need this type def. It will return this, and then it will, this is what it will be called. It accepts one argument, and that argument is also constant as 32 original function. Okay. And let's try to figure out what we will what we will do here. We need to, so we know that this original function is passed to us in RCX. So we will need to call whatever is in there. I'm just thinking if I should right now try to go into defining arguments for a function or not. I guess let's just first make it work, and then we will see if it does work. This will be a bit of a useless instruction. Like, we can say this should be optimized out, because the function we are calling already returns to us the value inside the right register, like inside arrayx, and this will just kind of try to move from arrayx to arrayx. I mean, which is the instruction that the CPU will happily accept, but it's not the instruction that you want to have in your program, because it doesn't do anything. Okay, so function begin, and then right now let's start with the raw encoder and then see if we can do something better. So we do encode function buffer instruction call, and the argument is this. The argument is RCX, which is actually no, that's not true. So I actually created the wrong way around. So this should not accept any arguments like this. This also doesn't do this, and instead we will need a new type. So the type of this will be proxy S32, and the type of this will be even more funky. So it will be S32 proxy S32, and it will accept constant S32. Yes, something like this. So we return a function that will accept a function that we will call and return whatever that thing returns. Yeah, that seems what I want. So we call that proxy with our, so first of all, let's fix this type. And we call this proxy with this. Okay, let's see how many mistakes I made. Yeah, that's fine. That's indeed not correct function. It should be proxy. Okay, that's actually built, but let's see what if we end up with correct instructions. So let me open the debugger and we'll just break over here before we return function buffer memory and see what is happening there. Okay, we can look at, I guess, something like this function. Function buffer, and then we need function here. Okay, that's fine. We have, what I'm looking for is ffd1, when it has it adds the rex prefix, which probably will not hurt, but we're not sure about it. Let's see if it works. So ffd1, and we have it here. If you look at these last 2 bytes, so ffd1, and you have the 48 prefix. I mean, looks fine to me, I guess. So this is return, this is add, this is move from RCX from REX to REX, that useless instruction, and then this is our call. This is sub. I mean, honestly, we can probably get rid of that RC, like move RC REX quite easily if we just go to function return and we say if compare, I never remember how to call this thing, but we'll figure out. I think it's like REX to return size of REX is 0. And so if size is not 0, then we need to do this. Or at least it's correct. Correct way to call it. Let's try that again with the encoding. So, okay, we still need to step over this. Oops. and blah, 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 blah. So yes, it skips the mem compare. And here we now don't have it, which is very nice. So instead we directly do subtraction of the stack and return. That's good. Let's see if that thing actually works. And it does. So this is very nice. Since I probably still have a bit of time, let's try some more stuff with different calls. But before we add this to index, so we don't lose this. Okay, so we were able to pass a function, and then we can call it from that other function, which is nice. The next thing that we can try to do is something that C doesn't actually have and that other languages implement very differently. And this is, we'll try to partially apply a function. I mean, why not? We have this make identity S64, and we will try to make kind of make constant S64 out of that make identity 64. So where is our constant defined? So we will need another thing that is going to be like constant S64, S64, S64. And then, so it will our function. So let me, with this way to specify functions, so it's a bit confusing what should go where. So we have our constant S64, and this is what we will return. But what we accept is identity S64. And actually, yeah, we don't even need this one. I guess we accept identity S64 in here. I call it original function. And we also accept, so make partial application S64. So, okay, we accept the function, we accept S64 as argument. And now it's actually pretty straightforward what we need to do, because we will need to store this function somewhere, and then we need to store the argument, and we call that function with this argument. So for the argument part, it is pretty straightforward. We just need to store it in RCX, so it will be move from, so I guess we'll need a stack stuff. With 64-bit operands, it's always a bit tricky, because I'm not even sure you can specify like a 64-bit immediate somewhere. Okay, so there is a version of this function that can specify immediate that is 64-bit and move it to the register. But I'm not sure I want to do this right now, because it will require us to implement this version of encoding where you just add the register to opcode, which might be a bit tricky. So let's just switch back to 32 bits because that will simplify things quite a bit, and we already have constant 32-bit anyway. So we will just need to have Um, will we need? I guess we'll need this the 32-bit version of identity, which honestly we can just cast the 64-bit version and ignore any discrepancies there. So that's fine. Let's define that identity as 32, which just is like this. 32, and then we say immediate 32 of argument. And then we need to call some function. So it looks like we will need to implement that move after all, because the problem is here that we will address of the function is full 64 bits, and we need to, and the only way to call this is through a register or memory, as you can see here. So there is call, yeah, and I'm not sure how to do that the best way. So I guess we can shove it into RAX and then call RAX. So we will need to implement that 64-bit immediate. So immediate 64 of this. If we are implementing it anyway, then we don't need this one, and we can move back to 64 bits here. 64, 64, 64, and then we call rocks. So this prepares the argument. This moves the address of the function in the right place, and then we call that function. Obviously, this will not even build, which is correct. So we do need constant s64, and it accepts nothing and returns s64. What's the problem? Yeah, so it doesn't know about immediate 64, which is fine. We just need to teach it about immediate 64. This is like this, 64, 64, doing more here and here. Now it should go into put it here, and we need to create this new operand type as well. We need to have this encoding here, where we output, where is it? Yeah, so where we output immediate operands, we now need to have an option to do that. And we append s64, that's fine. But one thing that we will need to implement is this new encoding type. And we say that it's called opcode plus register. So the way that works is you take this opcode B8 and then you just add a register number to it, which we have in our registers here. So we basically just take B8 and add, for example, 0, or you add 1, or you add whatever. We can even try to simulate what the output should look like. So we have move arrayx, and then we need this large number. That's fine. Yeah, so this is what the instruction will look like. It even has the rex prefix, which is good for us. It will be B8 34. And if we look into move, it is B8 plus register, but our register is arrayx, and arrayx is index 0, so B8 plus 0 is B8. So great. Encoding instruction type is code plus register. We don't have the opcode extension, so this is not what's happening. Extension type. Yeah, we will not have, so it's not really opcode and it's not that, so we need to also add this encoding to our I guess. So how does our routine look like? We go through these things, and then we if you find the register, then we do one thing. If we don't find the register, we do another thing. Coding type, and then we have match. Extension type, extension type. Guess I can do this for now. And I should not be editing this version of call. This is not what we are editing. Instead, we need to edit our move instruction. So it's a new move that is called B8. It has no extension, and here extension type, let's just add a new extension type, and that new extension type will be none. This one here, extension type none, and here we have also operand none. Actually no, this operand immediate 64, which we need to add here as well. And then we want to change this type to opcode plus register. Okay. That seems fine. Now we need to teach our staff to use this opcode plus register. Okay, so the match will find it. Here we need to add another thing for 64 bits. 64, that's also good. And finally, we need to say else if encoding type is this. Actually, if we put, oh no, it's fine. So we say reg or opcode is coding. No, it's not reg or opcode. It is, where is it? Yeah, so what we want to do, I guess, is take this opcode and put it in the variable. Code is this. Or let's make it U8 for now. And then here we just append it. But here, if we realize that we need to encode something in it, we just do like this, code plus equals and then register index. In reality, we'll need to do more. So to do use regs for bit for extended registers like R9. But that's fine, that's later. But right now we can do this. Okay, what is not fine? Function differs levels of indirection from identity S64. What? Which function? Ah, okay. Yeah, I forgot to actually return something. Okay. What is the problem now? Yeah, we have to cast this to S64. And finally, we have to change this stuff. Okay, it builds. Let's see what it actually does once we try to run it. I'm not even calling this function, so okay, because we didn't write a test for it, should create a partially applied function. And we will take this identity S64. And then we will take our make partial application. We'll pass the ID S64 to it. And we will pass 42. It will return to us constant S64. We will save it here. And that should be it. Good. Let's try to run it again. F. So this is fine. This is just the placeholder for sub. Now this is an interesting one. Move RCX and then a very long number. That seems fine. So we can try it here. I mean, it will sort of not look exactly the same. So I have to leave this one at the start. Otherwise it will not do what I want. So this is what we have, right? We have 48, B9, 2A, and so you can ignore this one. It's like all zeros. Okay, that seems to be encoded correctly. What about the next one? Next one is funky. There we can look at the address of original function. So this is the address, and it is little endian, so it is 0, 0, 8, F1, 5E, 0, 2. Looks like it's missing a 0, which is strange. Right. So this is 4. No, this is fine. But no, that's okay. All the zeros are in the right places. Okay, so we have that. Call should be perfectly fine because we already did that before. And we return stuff. Yeah, that seems fine. So let's see what result is. Result is 42. Look at that. It works. So let's watch it here. La la. So in about 45 minutes, maybe even less, we've added a way to call functions, but not only that, we also implemented something really neat, which is which is a way to partially apply a function. So to save an argument and allow it to be called from anywhere. And this is kind of really neat, because the way it's implemented, for example, in C++, is that you create an object and then call a method on that object with the captured state. And that means that you can't just take a lambda out of C++ and pass it to like a function that accepts an arbitrary callback. It's just not gonna work. Here, it sort of will. If we want to fully implement this version of capturing variables and partial application, we'll need to do some funky stuff where because function expects all arguments to be in certain registers, we'll need to do a bunch of moving from register to register or even from register to stack. But I still find it super neat that something like this works, at least in a simple case. So with that, thank you very much for watching and see you next time.